Hi, so this is a video to help you out with number 2 on the Connect homework for Chapter 6. It's a problem asking you to examine a neutralization reaction. You're given volumes and concentrations of an acid and a base. You're also given some other information about the system, the initial temperature, and some assumptions that you can make. And you're asked to find the final temperature of the mixed solution. And you're given the heat of neutralization, or the enthalpy of neutralization. And so this is pretty similar to what you guys did in lab, except in lab you measured the final temperature and found the enthalpy of neutralization. So let's think about a general strategy here. First of all, if we're going to find the final temperature, chances are we're going to have to think about the change in temperature and how, we'll start with the initial temperature and then add the change in temperature to it. Now, what do we know that relies on change in temperature? Well, the heat transfer. So Q, heat transfer, is equal to mass times specific heat times that change in temperature. So then, what else can we relate here given the information that was given to us and kind of where we're headed? Well, the enthalpy of neutralization, delta H, is equal to the heat transfer, but it's expressed on a per mole basis, so Q divided by N. So we are given the heat of neutralization. We can calculate N, and this might be the biggest stumbling block, but I'm going to go through that step by step. We're given all these volumes and molarities, and we know the chemicals involved, so trust me, for now we're going to be able to calculate N. That's going to allow us to calculate Q, and once we have that, we can substitute it into the second equation written. Mass will be able to calculate, specific heat we're given, and that will allow us to calculate the change in temperature. And once we have that, we're basically done with the problem, because the final temperature is just the initial temperature plus the change. So let's think about doing this problem in this order. We're going to start with this equation, then that equation, and that'll bring us up here. All right, so first of all, the enthalpy of neutralization. We are given a value here, but one thing we're going to need to do is think about this whole reaction. So let's write a balanced chemical equation for it. We've got nitric acid, HNO3. We've got barium hydroxide. And you guys have studied acid-base reactions. What happens when an acid and base are mixed together? Well, the protons, the hydrogen ions from the acid, are going to combine with the hydroxide ions from the base. That's going to form water, which has a neutral pH. And then the last thing that's going to be there is the salt. So we've got barium ions +2. I know they're +2 because they're in group 2 on the periodic table, and also because there's 2 hydroxides that are bonded to it in the ionic compound. And nitrate is -1, so I'm going to need 2 of those guys for every 1 barium. Just to save time, since it's kind of slow to write with this thing, I'm not going to draw in my states of matter, but we got aqueous solutions, H2O is a liquid, and an aqueous solution of barium nitrate. Now, let's balance this. I'm going to need a 2 right there. Let's see, that'll give me my 2 nitrates and my 2 hydrogens, and then we're also going to need a 2 on the H2O. Now, one thing that was given to us in this information about the heat of neutralization is that this is the amount of heat given off because there's a negative sign there, when 1 mole of nitric acid reacts with half a mole of barium hydroxide. So when that's the case, if we have 1 mole here and half a mole here, because the coefficient of 2 on the water is the same as the nitric acid, that means I'm getting 1 mole of H2O. So we can say that that heat of neutralization value, 56.2 kilojoules per mole, that per mole is, you can think of it in terms of per 1 mole of H2O, because that's how enthalpies of neutralization are defined. So yeah, that's our delta H. Okay, so next thing here, how many moles are involved? We're going to have to go back a few chapters and use some of our molarity and stoichiometry tools. So how many moles are formed? Well, we're going to first need to look at our reactants, at our hydrochloric acid, our nitric acid and our barium hydroxide, make sure there's no limiting reactants, or just allow us to calculate exactly how many moles of water are going to be produced. So first things first, if I want to calculate the moles of acid and base, my volume of the nitric acid, I can use molarity to help figure out how many moles there are. So it's 0.5 moles for every 1 liter of solution. I've got 230 mils, so I first converted that from mils to liters. Liters will cancel out, and then I'm going to end up with my moles of the nitric acid, and that's 0.115. Moles of HNO3. Okay, then for the barium hydroxide, it's also 230 mils. Also going to need to convert that to liters. And the molarity of this solution is only 0.250 moles. So that is going to give us 0.0575 moles. Of the barium hydroxide. Okay, so now the nice thing, I can tell because the volumes are the same and the molarity of the nitric acid is twice the molarity of the barium hydroxide, that these molar amounts are, there's twice as much nitric acid as barium hydroxide. And that's good because that's the stoichiometric ratio that the coefficients indicate. So that means that there's no limiting reactant in this problem. So the fact that, again, our coefficients of 2 on both the nitric acid and the water, that means that this combination of the two reactants is going to give us 0.115 moles of water. And so that's going to allow us to calculate exactly how much heat is given off. If I've got 0.115 moles of water, and I know that every 1 mole of water gives off 56.2 kilojoules of heat, that allows me to calculate that this particular amount of reactants in the equation, or in this experiment, that will give off 6.436 kilojoules, which is equal to 6,436. Sorry, I got my numbers backwards here. 6,463 joules. I'll write that on the next page a little more neatly. So yeah, that 3 and the 6 are swapped there. So if that much heat is being released by the reaction, what I can say is that the reaction, the heat given off by this reaction, I'm going to use a negative sign here because it's given off, is going to be absorbed by the solution, basically by the water and whatever else is in there, the salt in this case. That water that makes up the majority of the solution is going to be absorbing that energy. So what I'm going to do is set up an expression for heat transfer, mass times specific heat times delta T, and I'm going to say that I'm going to solve it for the solution, the water, and set it equal to a positive value of this heat transfer. So do this on this next page just to start with a clean sheet. So in other words, 6,463 joules, that was my value from the last calculation, is equal to the mass of the solution, which is 460 grams. I got that because we started with 230 mils, and I'm assuming a 1 gram per mil density. So that's my mass. Annotate that up here. My specific heat for water, because it's the water that's absorbing this heat, is 4.184 joules over grams times degrees Celsius. And then that's going to be times our delta T. So we know everything here except for delta T. So if I move things around here and just divide 6,463 divided by 460 divided by 4.184, my change in temperature is going to be equal to 3.36 degrees Celsius. And that means that my final temp is equal to my initial temp plus that change in temp. And so from here it's pretty straightforward. We've got 18.46 degrees Celsius plus 3.36, and that's going to equal 21.82 degrees Celsius. So hopefully this helps you attack this type of problem.